You guys that don't know who I am, Steve Suarez. I am the CEO of HorizonX, and I'm doing some other type work in the quantum industry. And I've got the pleasure to moderate today's panel on quantum sensing and how it's being used in the industry. I figure, who needs a measuring tape when you can use the nature to help you tell you where things are, right? All right, we're going to try to make this a little bit more. That was supposed to be a funny thing, so thank you, yes. See how that works? All right, good. So let's go down the panel. I'm going to ask each of you guys to introduce yourselves. We got 45 minutes, and so what I'm thinking for this panel is I'm going to ask a couple questions to the people here, some questions that I'm interested in to kind of learn more about this. But I am going to open it up to the audience and see what questions you guys have. So any question you want on this, it's a fascinating topic. And I could tell you one thing that people talk to me, when I tell them I'm doing things in quantum computing or in quantum, they say, oh, well, that's years down the road. You're not going to do anything valuable in quantum. But then, you know, we separate two things, right? We separate quantum computing from quantum technologies. And the good thing about quantum technologies is people are using it today. So did anybody use Google Maps to get here today? Can you raise your hands? A lot of you. You know, you guys used quantum technologies to get you here, and we'll be able to kind of explain that here in a bit. So, Tim, why don't you go ahead and start? I didn't want Tim sitting next to me because he's so tall. It just makes me look so small, but there he is. All right, Tim, please.
Yeah, sure. So I'm Tim Pryor. I'm from the National Physical Laboratory in the UK. My whole career has been about measurement science and using that knowledge to solve problems for either industries or government. We've been involved in quantum really since quantum was invented, in that one of the first applications or the first thing to develop quantum has been measurement science. So we've used it for years and years and years. So when it became something that people thought was going to have an application in general sense, we were very well positioned to actually begin to offer our experience with that. So in the UK, we're a metrology lab where we do measurement science, and we do that across all the elements of quantum, from computing through to sensing. And we have a sort of unique role in that we try to understand the things that allow people to compare technologies. We try to understand the background so that if people come in, they can think about how they can improve performance because they can measure the performance as it is.
Thank you, Tim. Very, very fascinating. Mark, would you mind kicking us off?
Thank you. I'm Mark Fromhold from the University of Nottingham. My background is in semiconductor physics. So I did my PhD in semiconductor physics. Then I switched fields completely. I worked in a hospital as a medical physicist where I was involved in brain imaging, and I had no idea that 20 years later I'd be back involved in brain imaging through quantum technology. So having returned from the hospital environment into academia, I got fascinated by ultra-cold atoms. That led into quantum technologies, and in particular quantum sensing. So now we're working on sensing of magnetic fields, gravitational fields, rotation, and in particular my focus at the moment is on electromagnetics and commercializing electromagnetic systems that are needed for a range of quantum sensing applications and also applications outside the quantum environment.
Excellent. Thank you very much. Nima.
Hi, I'm Nima Leclerc. I'm a research scientist at MITRE, a federally funded research and development center in the Boston area. And we sit in a really unique place. We're technically a government lab run by a private company, and we execute R&D projects across various emerging technologies at the intersection of government, academia, and industry. I lead an effort, in particular, working on wide field imaging systems using solid-state quantum sensors, diamond-based quantum sensors, which I'll get into later. And yeah, prior to this, I'd say like I'm a semiconductor person at heart. I've spent my entire career so far working on semiconductors for new computing technologies, both classical and quantum. Graduate work in silicon quantum processors and at the University of Pennsylvania. And prior to that, my background is in material science.
Excellent. And so we decided to put the finance guy all the way on the end. I'm an ex-finance guy, so I'm a recovering banker. But Tamid, why don't you give us an introduction on your background?
No, thank you very much. Hi, I'm Tamid Kudis Islam. I work at Citi Global Insights, which is Citibank's thought leadership division. By means of a quick bit of background on me, so my background academically actually is in astrophysics, and my initial job was in the European Space Agency. So I helped write a lot of different reports on innovation and technology at Citi, ones on space, for instance, AI, the innovation landscape as a whole, blockchain, digital policy, and of course, quantum computing and quantum sensing. Quantum is very much one of my favorite topics. I was fortunate enough to lead Citi's recently published 150-page report into quantum computing and our 50-pager into quantum sensing. We're in quite a unique position in that most of our content is really publicly available. So my job, as I see it, really is to kind of inform and educate the public and help spot these emerging and disruptive trends.
Excellent. Thank you very much. My first question is going to be a question to all of you, so you guys can kind of see who wants to go first. And part of it is I want somebody to demystify quantum sensing. I mean, maybe everybody here is an expert and everybody knows exactly what it is, but help me demystify this technology. What's the potential of this technology? Why should anybody in this room care? All right, Tim.
So I think the first thing to focus on really is the word sensing. I mean, we have so many sensors. It came up in previous talks. You know, we are surrounded by sensors. Sensors enable our whole world. So we should be interested in sensors. But why quantum? Quantums offer us the ability to do things that we've never been able to do before, or do things more accurately than we've ever been able to do before. And that is such a huge potential. So you've got this huge application area with a new technology that's enabling us to do things we've never thought about doing before. And I'll let some of my more technical colleagues say something on it, but I'll just give you one example of something we were working on at the moment. So we noticed that when we were doing fiber optic transfers between countries, that occasionally we could see traces of things. And we actually looked at that, and we realized that that's when earthquakes were happening. So the underwater fiber cables, intercontinental cables, we could detect earthquakes. And so we're now looking at using those techniques to potentially be a worldwide warning system for doing earthquake detection, tsunami detection much earlier than you could do in any other way.
Yeah, please, Mark, go ahead.
Yeah, I'd say forget the quantum and think about the applications. And there are many application areas in contemporary science, contemporary problems actually for humanity. So for example, climate change. If you want to know the rates at which icebergs are melting, you can look at the thickness of the permafrost. One way to do that is by measuring variations in gravity from satellites. Another problem, neuroscience, dementia, all sorts of neurological diseases. Colleagues in Nottingham have set up a company, Circumagnetics, which is now making brain imaging systems that relies on the ability of quantum sensors to produce magnetic fields produced by our brains when our brains work that are about 100 million times smaller than Earth's magnetic field. And that's leading to all sorts of abilities to image what goes on in our brains when we move around, when we interact with other people, as our brains develop. So it's applying it to pediatric neuroscience. And there's tens of millions of pounds of exports now of these quantum brain imaging systems that are going on. So again, it's a tool for understanding things that are of importance for all of us, really.
Excellent.
Yes. So I'll try to go from like microscopic to macroscopic. In my opinion, a good definition for a quantum sensor is a device that uses quantum objects or quantum mechanical degrees of freedoms like electrons, electron spin, photons, and leverages their sensitivity to their environment to get orders of magnitude gains in sensitivity in basically measuring the world, in detecting and measuring the world around it. These things that you sense can be really broad. They could be magnetic fields, they could be electric fields, they could be gravitational fields, all these sorts of things, but they could do them orders of magnitude. They could provide orders of magnitude improvements in the amplitude of the signals they're able to measure, the spatial resolution, the temporal resolution, because you're really using a sensor at the atomic and at the length scale of atoms and individual electrons. Sort of tying this to applications, so one thing that I'm involved in at the moment is leading this effort developing these magnetic field imaging systems. So what we're really interested in is understanding the activity of what's going on in the interconnects of chips as they're running computation. Whenever a current flows through an interconnect in a chip, it emanates a magnetic field, and that magnetic field is very small. In fact, about like 100 million times smaller than the Earth's magnetic field. And for that, you need a really accurate sensor. Not only do you need to sense that magnetic field, you need to do it with really good spatial resolution. So working with some colleagues at MIT and Harvard, we've developed a technique to actually image these magnetic fields in real time to really understand the computation. I think this also transcends to other application spaces, like in biomedical imaging, as you mentioned. Really anywhere where you need to sense some really small signal with good spatial resolution.
And Nima, I think what's interesting there is that it's non-destructive, right?
And it's non-destructive. So you could treat this, I mean, we actually call it the quantum diamond microscope because we put a piece of diamond on top of a chip and we're able to image the activity of what's going on in the chip without actually opening up the chip. And we're actually working with some folks in the microelectronics industry to see how this could be compatible with other existing approaches that are used to sort of reconstruct microelectronic circuits.
Thank you.
Yeah, so I'd say in terms of what is a quantum sensor, what is quantum sensing, if quantum physics is the physics of the very small, when you look at things on an atomic size, I think it's about kind of understanding that there are counterintuitive phenomena that you see. So atoms can be, as I'm sure many of you already know, act as a particle or act as a wave at other times, and they can interfere with themselves. So I would say, personally to me, a quantum sensor is a sensor that explicitly exploits this quantum phenomena, typically to take measurements of properties and do so. They don't have to, but the kind of commercial aspect is for them to take measurements that might be more precise, or be able to take more sensitive measurements, or be perhaps offer better stability or better kind of cost or weight reduction. So I'd say that's kind of what I would consider as a quantum sensor in general. I would caveat that with, I just came from a NATO workshop on quantum sensing, and we kind of agreed that there isn't a fixed definition of a quantum sensor, as opposed to, with quantum computers, I could outright tell you that's a quantum computer and that's a classical one. I would say two things. One is, firstly, in terms of quantum sensing, I really consider it an umbrella term. So I think there's 5 or 6 different kind of quantum sensing technologies. You kind of have atomic clocks that measure time, quantum magnetometers that measure magnetism, quantum gravimeters that measure gravity, quantum inertial sensors that kind of look at kind of your movements left, right, up, down, backwards and forwards, and rotation. You also then have kind of photon detectors that measure individual packets of light, known as photons. And what I refer to in the report as quantum electrometers, but I'm sure my colleagues will probably point out, they're actually kind of quantum radio frequency sensors, which you can take a guess what they sense. I think why we should be excited about all of this, and I'm sure we'll dive into it in a bit more detail, is because we live in a world where data really is king. And if we think about the phrase, data is the new oil, what quantum sensors allow us to do is to collect kind of an understanding of the world at a deeper level. So by having kind of more deeper granular measurements provided by quantum sensors, we can get more deeper granular data, and that can better inform our decision making.
Excellent. Yeah, go ahead, Tim.
So just another comment on this. Well, I think the term demystifying isn't actually that necessary for the majority of people once we start describing what it does rather than what it's called. And I think that by the point when we start saying that, this is a thermal detector, this is a magnetic sensor, this is what it's doing.
Yeah.
The mechanism of how it achieves it to the majority of people is irrelevant.
Yeah, no, I think it's a good point. But how it gets done is actually, if anybody can explain it. I think Einstein called that, spooky action at a distance, because even Einstein had a hard time kind of explaining how quantum mechanics works. And he wasn't, if I remember right, he wasn't too happy about it, and he was always trying to disprove how it is, and he wasn't. And funny, I just got paged by somebody, and I'm playing word bingo, and they said, "Can you get the word submarine in your presentation?" So are you guys allowed to talk about submarines or how this
It's
technology?
not advised, I think, is
Yeah.
the...
Submarines are a no-go.
You can't talk about submarines?
No
Is that
go.
because
I'm
you're,
not.
anybody else talking about how submarines can use this technology? Help me out, because I'm trying to win this word bingo here.
Navigation. Navigation.
Okay, navigation.
I'm looking at somebody in the audience who knows all about it.
Oh, does it? But
Yeah.
you just pointed at that someone. Actually, hopefully they're not classified. But yeah, no, I mean, I heard interesting how submarines can use this to actually navigate. Are any of you guys allowed to talk about this, or is it, I get you in trouble?
I think one of the great things about the sensing in terms of position, navigation and timing is it enables vehicles to have an independent source of where they are, where they're going, etc. And that's not spoofable, that can't be jammed. So you can have a really good idea of what's happening. And that could be applied to vehicles on the land or in the sea.
Excellent, excellent. Thank you very much. Thanks for letting me.
Submarines in case, yeah.
Hold on, Mark, go
I
ahead,
was
Mark.
going to say, if you Google nuclear submarines, you'll find horror images of submarines whose front ends are caved in because they've hit other things. And so precision navigation underwater over months is really, really important to avoid that.
Thanks for letting me get these points. It's good. I shut it off so I won't get any more for the rest of this meeting. But yeah, all right. So, Tom, I'm going to go to you. I'm going to go straight to you and ask you. You're the finance guy here. You're the one with the money, right? Why is somebody from Citi sitting here interested in this, and where do you make money from this?
So we're quite in a unique position at Citi Global Insights, being Citi's thought leadership division. And I think kind of our position has changed over time. Initially, as I touched on there, it was kind of to look at the latest trends, which is why we looked at kind of quantum computing. But as we kind of became more familiar with the technology and where it is placed relative to other innovations, we realized that actually quantum sensing is something that in some respects does need demystifying, right? It's about 5 or 6 different technologies. So kind of our initial aim was to kind of inform and educate, which is why we made, all our reports publicly accessible. But kind of as we've progressed, what we've decided is actually, we can help the ecosystem a little bit. So, from our perspective, we think it could be a win for everyone. So for our clients, knowing, what are the latest trends, for the public to be kind of informed and educated. And in terms of the ecosystem, for instance, so Citi recently joined UK Quantum, which is the voice of the kind of quantum industry in the UK. And we've actually just also recently joined the steering committee of that as well. So we really think it could be a win for everyone, and or at least that's the aim.
Excellent. So let's talk about the supply chain, because I know working in quantum and working in sensing, supply chain could be an issue. And you got the quantum computing side and you got the quantum technology side. Are there opportunities to leverage components from each? And are there any bottlenecks that make scaling this technology difficult right now? Who wants to go first? I could see you're ready to go. So.
I could comment on this. So I've had some personal experiences with supply chain issues. So for a while, the diamond seeds that we were using actually came from a company called, I think it was New Quantum Technology, based in St. Petersburg, Russia. I think there are obvious reasons for why that's an issue now. But a lot of research groups were actually depending on this one company in St. Petersburg to get their diamond seeds. And I should note that the diamond seeds that we need for our quantum sensing applications have very stringent requirements. We need to have very high defect densities. So the defects are actually what are enabling the magnetometry scheme that we're implementing. We also need there to be very low defect densities for other defects that we don't want. We don't want isotopes, so all of these things. And it turns out that many of the other companies that are making manufacturable diamond are actually catering to the gemstone industry. So they're not up to par with the quality that we need for very high sensitivity magnetometry. So I was involved in an effort recently working with a group at MIT Lincoln Laboratories, and actually an Oxford-based startup company called Element 6 to see if we could come up a way to have supply chain resilience for diamond that would be used in quantum sensors. And we were able to work with the Department of Commerce in the US to acquire money from, well, we haven't been able to acquire money, but we've been trying to acquire money from the CHIPS Act to really scale up manufacturing of diamond and sort of do it at a scale beyond just a national lab and an academic lab. These efforts are still ongoing. Apart from the materials, I'll also say that the control electronics and the photonics that are used to actually miniaturize these sensors, so not the sensor itself, but everything you use to control and read out the sensor, also have really complex and intertwined supply chains that we need to think about more carefully.
So at NPL, we've run quite a few workshops with industry to try and understand what problems they face in terms of building their businesses. And first of all, skills comes up. I'm not going to address that one here. Supply chain comes up. But the third most popular thing when we ask it is standardization. And actually, I see both those things going together, supply chain and standardization. Until we have a common language to describe components, until we have a common way of testing, it's almost impossible for some areas to actually order the parts they want and know they're going to get what they expect to get. So that's a question for national labs like the National Physical Laboratory, and we lead in the UK on standardization. But it's a question for industry in that we really need industry to engage so we know what they want us to go and sort out or help to sort out. So that's a call out to people. Think about things like standardization. As you're developing your products, if you wait to the end point, someone else would have put a standard out that might exclude your technology.
Yeah. Go ahead, Mark. Go ahead.
Yeah, I mean, there are loads of opportunities, I would say, for companies that are not quantum as such, because all of the components that are needed for, say, quantum sensors, quantum computing are used in other areas already. Things like vacuum systems. There's a huge, in the UK, big vacuum industry around Sussex, for example, ion pumps, lasers, optical interconnects, electronics, interfaces. All these things are sort of standard across many sorts of technology. And really what's needed for quantum is the ability to bring them together, miniaturize them, reduce swap-C, and so on. Chip-based things are really important. And actually, we heard earlier about work going on in Austria, the Austrian quantum community. We're working with Austrian Microsystems to develop chip-based traps for atoms that use entirely standard CMOS fabrication. So to try and tap into that established semiconductor supply chain and adapt it for quantum.
Excellent. Tamid?
Yeah, I'd say, I think it depends what types of quantum sensors you're talking about. So if I just take an example, if you look at, quantum accelerometers and then compare that to like quantum gravimeters, when you talk about measuring gravity, what are you talking about? Typically measuring the acceleration due to gravity. And with at the slight risk of potentially annoying a few people here, fundamentally it's kind of the same instrument. I know technically it's not. There's a lot of different differences in the engineering. But what are you measuring when you're measuring gravity? You're measuring the acceleration due to gravity aimed downwards, right? So in that sense, yeah, there's probably going to be a lot of overlap in the supply chain there. But then there will be other quantum sensing technologies, let's say, photon detectors that don't overtly have a clear kind of overlap with, different types of quantum sensors. So I think you need to, when you think about it, think about kind of which sensors you're talking about. But of course, throughout kind of the quantum sensing umbrella, you could argue there are definitely a lot of similarities. For instance, a lot of these sensors need to be super cooled.
Yeah. Excellent.
The ones we work on are room temperature.
So actually, one of the things we get asked in our laboratory is to do testing on standard photonic type components or RF components, and actually, will they work very closely inside a fridge? So, and once they've been tested in those environments, that suddenly opens up and they can times 10 to the price and put a quantum in front of it.
Interesting. Nima, I've got the question for you. Tell me about the private-public partnerships. I know you said you're based in the U.S., so maybe tell me what's going on in the U.S.
Yeah, so I think there are three models that I've personally been involved with. So the first is small scale. So I'll go small scale, medium scale, larger scale. So this is when an entity like ourselves would partner with a startup company or even a larger company. So the one I'll call out is called Euclid, that is a spin-off from Ron Walsworth's group at Harvard. They're now in the Maryland area. And they're developing the same technology as us. They're developing this quantum diamond microscope. And they run into the same technical challenges that we do. But they struggle to find customers, especially in the government sector. So one place where we could offer an advantage is using our connections with government agencies, specifically in the Department of Defense and intelligence agencies, and sort of identify government end users. And then we sort of work side by side with both the government, our internal team, as well as the startup company to identify the government needs so that we're developing a technology that's actually useful for an end user. So that's one route I've seen being pretty successful. The other scale is what I mentioned, where you have like a larger collaboration between private partners, so like smaller companies or larger companies, academics, as well as government labs or government agencies. So I think a great example of that is that CHIPS Act effort I was mentioning. So there we were trying to achieve a very ambitious goal, which is to establish supply chain resilience of diamond material for quantum sensing. So that really requires a large effort at the tens of $1 million level, which individual research grants can't really supply. So we brought together a much larger team there, including about I think 20 collaborators. And then we approached the Department of Commerce proposing them this problem, explaining why it's important, why this is a national security issue for the US, then started having conversations. And I think that's another stage of private-public partnership where it's not formal. You don't really have a formal proposal process, but it normally starts with a conversation. You bring together a team of people who folks from industry, folks from academia, and folks from the government, and using your connections, you approach the relevant government agency. The last one I'd say is more informal, but at a much larger scale, and this is in developing a quantum ecosystem. So we have something called the Quantum Economic Development Consortium in the US, and this was founded under the National Quantum Initiative, I think in 2017. And this is more of an informal collaboration that brings together all parties, so VCs, industry, government, academia, everyone. They hold regular workshops on different quantum technologies. So that's just to keep everyone informed and to sort of provide a network of people that could sort of co-develop technology together. The other part is workforce development. So QEDC also has a large effort in sort of translating the skills of microwave engineers, photonics engineers, really people at all skill levels, all the way down to community college graduates, to see how they could join the quantum workforce and be part of this ecosystem. So overall, I've seen, private-public partnership be quite lively in the US.
Excellent, excellent. I'm looking at the time, and I want to ask one more question. So Mark, I'm going to go to you really quickly, if you can tell us about the UKQT program.
Oh, yeah.
And then I'm going to open it up for questions, and I want you guys to get your questions ready. Make them really tough, because these guys are really smart people. I want to give them really tough questions. Thank God that I'm not on this panel speaking. I'm just a moderator. So get ready, guys. Go ahead.
Okay, yeah, so the UK Quantum Technology Programme started about 10 years ago with £1 billion of government investment. And we were told at that time that this was not going to be business as usual from the point of view of science and tech development in the UK. And the whole idea of the programme was to take known quantum physics but translate it through engineering into commercial developers and end users. So it's created in that 10 years an ecosystem. You've mentioned the word ecosystem. It's really created a very broad ecosystem of hundreds of researchers and organisations, including universities with researchers from different backgrounds, engineers, physicists, chemists, mathematicians, working with industrial partners. An industrial partner that we were working with actually since the start of that program 10 years ago said to us then, what we don't want is for you to throw technology over the wall at us in 10 years' time. We want to be involved in the development of it right from the beginning. And that's actually happened. And it's been a real step change, and certainly in the way that we've done research and tech development in universities. It's involved collaboration with people like National Physical Laboratory, Rutherford Appleton Labs, and so on. And there have been a lot of successes of this program. So something like 100 companies now are working with academia and with one another on developing products and services. And that includes 50 startup companies spanning all of the areas of quantum technology, actually. And you mentioned skills. Skills has been really at the center of the program, and already that's led to the training of about 400 PhDs in the quantum area. So it's really set the UK up pretty nicely.
Yeah. Well, there's an opportunity in skills. I read recently for every 3 quantum positions that are out there, there's only 1 skilled candidate.
Yeah.
Which both is a risk, but an opportunity for people that want to get in this and really skill themselves up. And I'm sure we'll be talking a little bit more about that tomorrow. All right, so we got 6 minutes. Really hard question. So who's got a really hard question? Just stand up and ask your question.
Not too hard though, it's all right.
No, really hard. Even if it includes maths and stuff like that, because I got these.
Please solve this equation.
Yeah. Now, they bet me that nobody would stand up and ask a question, and I told them I knew this audience would. So somebody, any questions, any comments, quantum sensing? Who's going to be the first brave soul to... All right, there we go. Well done. Everybody, do me a favor, give this guy a round of applause, please. Thank you, thank you.
I have a tough question to you. You mentioned that quantum computing actually is increasing accuracy, might increase accuracy of solutions for businesses. So, but how does this interfere with fault tolerance, which we discussed before in previous section? So, if technology is actually not really accurate, so.
Mark, you want to go first?
Yeah, I would say that in quantum sensing, it's not necessarily the problem with the sensing, it's more with the environment. So, for example, if you're trying to measure magnetic fields around a person, you've really got to switch off Earth's field and switch off all that interference, which requires a lot of mu metal, a lot of active cancellation, and so on. So it's sort of getting the noise down in the environment rather than in the sensor itself, in contrast to a quantum computer, where it's the computer where you've really got to get the noise down.
Yeah, so we're developing some new techniques in actually controlling the systems in a smarter way. So actually the sensors I work with use a set of optical pulses, so laser pulses, and also microwave pulses. The way you actually send the pulses and the timing and the shapes of the pulses can all be mathematically optimized to reduce sensitivity to noise in their environment. So let's say you know what your noise source looks like. It could be a very high frequency noise source. You could actually set up your problem in a way, like in a mathematical way, where your goal is to optimize the sensitivity. You want your sensitivity to, it's counterintuitive. You actually want it to be very low because you want to measure very small signals. But you could actually mathematically optimize your pulse sequences in a way that the shapes of the pulses cancel out the noise of interest. So there's that, and then there's also just literally playing around with the instruments in the environment to cancel out any obvious sources of noise. So yeah, noise is definitely a big issue for quantum sensing. We don't call it fault tolerance, or we don't use the same language, but noise, yeah.
I wanted to kind of just, I know there was another hand up. Yes, please.
Hi, Tim. You
I have.
mentioned MPO leading on standardization in the UK. Can you explain more?
Yeah, sure. So in the UK, when we're talking about standardization, we're talking about this whole broad range of things, from establishing how the science behind the measurements, right through to documentary standards. We're also comfortable with green terminology, etc. So in the UK, the people who are most associated with standardisation is British Standards Institute, and we work very closely with them on a pilot to see if we can actually work more efficiently in terms of standardisation. So we're working very closely with BSI and other agencies in the UK to actually encourage people to work on standardisation, and then we can respond to the requirements that are coming out from industry. The worldwide thing is actually there's a new joint technical committee that actually is being run by BSI. So that's an incredibly important thing for quantum technologies in terms of how it'll be accepted in standards worldwide.
All right, I just realized, and I didn't know, we have actually questions right on the board, so silly me. We're going to make these really short, quick answer stuff. Can quantum sensing work in space? Anybody?
No reason why not.
I saw a no and I saw a yes. That's.
Oh no, that was a yes from me.
Oh, that was a yes. Okay, you
I just
did a no.
don't know.
Okay, good. So yeah, that was quick. That was too quick. Actually, you're going to do a little bit better than that. When do we expect quantum sensing to work on the phone? Somebody wants to actually measure something from their phone, and on cars for P&T, precision, navigation and timing. So I should know.
All right, so I can't talk too much about kind of automobiles as such, but if I give a quick example, I think we already have quantum sensors that work now today. It's just a case of getting them to the point where they're cheap enough to be used in industry. Look, if you stick to kind of inertial sensors, for instance, TfL, Transport for London, is investigating using it on the trains underground to see if they can pinpoint their location. If we talk about water, on the water, not below it, the Royal Navy, the Royal Navy is looking at using it to kind of identify where their vessels are in hostile environments where GPS might be kind of jammed. And actually, if we look at aerospace, one of the interesting things that we estimated in the report was, according to research houses, the quantum sensing market is maybe worth $500 million or so, supposedly. But we calculated, and this was before the government announced, I should point out, their recent kind of foray into using kind of PNT or quantum inertial sensors on planes. We estimated it could be a market of around $3.5 to $5 billion just in one specific type of quantum sensor, that is inertial sensors, in one specific use case. So I think there's definitely a broad remit, broad area, and that's before you even get onto the point of having, look, what's the secondary impact on kind of the economy and society, which is quite vast.
Excellent. And you could tell in his face he wanted to say the word submarine, but he held it. I saw it there. All right. So listen, we're down to the last 5 minutes. I want to make sure we end on time. My last question, and I'll just go straight down. You guys have about a minute each. What do you want to leave these people with about quantum sensing? Kind of maybe something inspirational, something to look forward to? Or what should people in here know when leaving this room?
So, I mean, one of the things that's really important to think about is actually quantum sensing is here. It's been here for a while, but it also has huge potential. So it's not solved everything. But when people are working on this, they really need to think about doing everything in parallel. So you need to think about if you want to scale things, you want to think about supply chain, you want to think about standardization, you want interoperability. All these things have to happen in parallel, because otherwise someone else who is doing it in parallel will get there faster than you.
Thank you. Mark?
I would say that, again, forget about the quantum and think about the multiple applications to real-world problems. And if you look at the McKinsey report, the market that's predicted by 2035 in quantum computing alone, let alone in sensing and the other areas, is around $1 trillion. So there's a huge financial incentive.
With a T, not a B.
Yeah,
wow, that's amazing.
Big financial incentive, but more important than that, big societal impact of these sensors, be it on healthcare, be it on climate change, or be it on security. So I think it's those societal transformations that are important here.
Excellent.
Yeah, I want to touch a bit more on the market. So as mentioned, quantum sensors are here today. They've been around for several years. In fact, they're systems in hospitals that use something called a SQUID, that's a superconducting magnetometer for magnetoencephalography. I think there are a few issues. One is in scaling, so we need to sort of work as a field to try to miniaturize these systems. So that means on the photonic side, figuring out how we could make photonic integrated circuits, sort of taking inspiration from Jeremy's talk earlier today, compact and integrated with the electronics that are used to control the sensor and also the sensor itself. I think the other part of this is also making quantum sensors a commodity, in the sense that we need to find areas that have very large markets that we could target where quantum sensors would be essential. And this has happened in the past with transistors, where the first application of the transistor was actually the hearing aid. And then after, so it was first used as an amplifier, then it sort of got reapplied to logic devices, and then suddenly it became a commodity. So I think as a field, we need to have scientists sort of being aware of all of the sectors and working sort of synergistically with, with other people in the business world. I know I'm short on time, so I'm going to pass it on.
Yeah, we're getting the blinking light, so now you're stressing me out. So, all right, go ahead, Tom. Take your time. Go ahead.
So sorry, what was the question again?
Think about the future, or what do you want to leave the audience with? In other words, in this topic. Yeah.
I would say, come back to my earlier point of if data is the new oil, quantum sensors are a tool for collecting that data, deeper insights, and allowing us for kind of better decision making. If there's one point I'd like to leave everyone with is that, we don't have anything to sell at City Global Insights, so when I say I think quantum sensors could be technology's kind of new eyes and ears, I really do mean that. And then one final thing, because it is really blinking,
I'm with you.
is to say that when you think of quantum sensors, think more. I know it's kind of frightening. Think as broadly as you can. Like the market size, the numbers you hear quoted might be relatively modest, but honestly, the societal and economic impact in the long run could be vast.
You're going to have to speak faster. All right. Yeah. I'm just kidding. All right, guys. So a quick plug. In 30 minutes, if you want to know what time as a service is, or I sell time, come back in here. We've got another panel to talk about this fascinating topic. But right now, I want to thank my panelists. I think amazing stuff. I learned a lot kind of through this process. I know we did, sorry for the curveballs, but I thought it would keep everything interesting. So why don't you give a round of applause to our panelists.